Welcome. Today we're going to talk about how to link up our work in formal matters, either first order logic or our probabilistic enhancement of it through non-monotonic logic, how we're going to hook up that information with what kind of attitudes and beliefs human beings ought to have, or for whom it would be good if they had them. So our target is to try to get to the point of probabilism. But before we get there, the first thing we ought to start wondering about is, how does any of this hook up with, let's call it the rationality of belief, or what the appropriate things are to infer from the new information that you receive. After we do this, we're going to go through and look at various ways of enhancing probabilism to try to get a meatier, a beefier, a more substantial set of requirements on people for being rational. Or, as I would prefer to think about it, getting more and better requirements that if you satisfy them, you'll do a better job of getting to the truth and avoiding error. Now, there are complications here on the path to probabilism in epistemology that are tortured and tortuous. It's very hard to get to probabilism at all, and we're not going to go into all the epistemology that underlies that. But I am going to show the first step and then the second step from the Teitelbaum book, and then we'll see where we can get from that point on. So the first step is we have a first order logic. It is a theory of the notion of logical consequence of a certain sort, namely monotonic logical consequence. It's a pretty good theory. It's not without its objectors. How does it connect up with the rationality of belief? Well, the answer is found in the Teitelbaum book. I'm going to share with you the screen from part of the Teitelbaum book that I think is absolutely crucial for understanding the first step here. It hooks up the rationality of belief with the notion of entailment. The notion of entailment is precisely the notion of logical consequence that we studied with first order theory. Okay, now look, this is section 2.4 of the Teitelbaum book, and I want you to look at the notion of comparative entailment. It is the first minimal step. It is short of probabilism, but it's the first minimal step at linking our investigation of the notion of logical consequence with the rationality of belief. Comparative entailment says, for any pair of propositions such that the first entails the second, rationality requires an agent to be at least as confident of the second as the first. Now, I want us to think for a moment about why such a principle might be plausible. So don't think so much about whether you can look smart or be smart or whatever and violate this. Just think about drawing a picture of the logical space in question. So we're interested in cases where P entails Q. So let's draw a picture of the logical space for Q. Now the question is, where does the logical space for P fit? Is there any part of the logical space for P that is outside of Q? So for example, could you do this and say, well, P entails Q, and that means that P overlaps with Q at some point. Well, that can't happen because then you've got all this part of P that is outside the Q box, and so P doesn't entail Q. So that's a very bad idea. So let's say, oh, that's not going to work very well. Let's draw some other pictures. Let's start with our box for Q. Our Q box looks like this. And what does our diagram look like when it's also a diagram of P entailing Q? The answer is every part of P has to be inside the Q box, because this says if P is true, then Q is true. Now, P could be as large as Q itself, but it cannot be any bigger. It cannot cross the boundaries of the Q box at any point. Otherwise, it won't be true that if P is true, then Q is true. So now think about being a person who's trying to figure out the truth. If you believe P and P entails Q, then P can't be true without Q also being true. So if you want to maximize your discovery of truths, if you believe P, you'll want to believe Q as well, if Q is entailed by P. Now, suppose instead of talking about full beliefs, the binary category of either you believe it or you don't believe it, let's think about degrees of belief. So to what degree are you convinced that P is true? You should be convinced to at least that same level that Q is true, because P can't be true without Q being true. So if your interest is in calibrating your levels of confidence with what's true or false about the world, your confidence level for Q should be at least as high as that for P. That's what comparative entailment tells us. For any pair of propositions where the first entails the second, you should be at least as confident of the second as the first, because the entailment claim tells you no part of the logical space for the first lies outside of the logical space for the second. Okay, now suppose you agree with that. Take a look. Take a look at how we establish the comparative entailment claim. Here's what Teitelbaum tells us. We've now introduced Kolmogorov's probability axioms as a set of norms on credences. So the probability axioms were things like the probability is strictly between 0 and 1. For any necessary truth, the probability of that truth is 1. For exclusive disjunctions, you can calculate the probability of the disjunction just by adding the probabilities of each of the disjuncts. So those are the axioms. He refers to them as the Kolmogorov probability axioms because probability theory, even though it was discovered by Pascal, the history of mathematics is that axiomatizations usually appear much later than the original discovery. So we're familiar with Euclid's axiomatic system for geometry. That's a pretty old and ancient one. Kolmogorov's probability axioms, I think they were published in the 1930s. I have a vague memory that it's 1936, but I could easily be wrong about that. But in the 1930s, Kolmogorov axiomatized what Pascal had discovered a couple centuries, 3 centuries earlier, 2.5 centuries earlier. This isn't unusual. The axiomatic system for arithmetic is given by Peano in the 1800s, which is astonishingly late given that arithmetic is one of the earliest mathematical systems to be well understood, well before the Greeks. So axiomatic systems are pretty cool, but they're not required for having a good understanding of the particular mathematical field in question. Anyway, so Kolmogorov axiomatized the probability calculus, and we can take those, if we want, as defining a set of norms on credences. Credence for Teitelbaum is some precise number between 0 and 1 that measures your degree of confidence in a particular claim. So if you're 70% sure you're going to win a lottery, your credence will be 0.7, that you win the lottery. Okay, so suppose we have Kolmogorov's axioms and we're looking at this comparative entailment requirement. Look at the second to the last paragraph on the page. Comparative entitlement can be derived from the probability axioms. We've already seen that by the entailment rule, if P entails Q, then rationality requires that the probability, that the credence for P is less than or equal to the credence of Q. But how much of the probability calculus can be recreated simply by assuming that comparative entailment holds? We saw in chapter 1 that if comparative entailment holds, a rational agent will assign equal maximal confidence to all tautologies and equal minimal confidence to all contradictions. Remember, tautologies cannot fail to be true. Contradictions cannot fail to be false. So if probabilities fall between 0 and 1 inclusive, nothing is worse than a contradiction, nothing is better than a tautology. That's why necessary truths get assigned a probability of 1 and contradictions will get a probability of 0. This doesn't give us specific numerical confidence values to contradictions and tautologies because comparative entailment doesn't work with numbers. But the probability axiom 0 to 1 scale for credence value is fairly stipulative and arbitrary anyway. The real essence of normality, contradiction, non-negativity, and maximality can be obtained from comparative entailment. So let's make sure we understand that. Normality is the claim that probabilities are found in the interval between 0 and 1 inclusive. That was the very first axiom we looked at for probability theory. Contradiction is that the probability of a contradiction is 0. Non-negativity tells us no probability can be lower than 0, and maximality tells us that no probability can be higher than 1. And all of those fit naturally with comparative entailment. Okay, so suppose you start with comparative entailment. It looks like you can give good explanations why a number of the axioms of probability theory should hold. What doesn't comparative entailment sustain? The answer is what Teitelbaum notes next: finite additivity. Finite additivity is the rule that I called the restricted disjunction rule, that where A and B are exclusive of each other, the probability of A or B is just the probability of A plus the probability of B. So this is what Teitelbaum focuses on. That leaves one axiom unaccounted for in the Kolmogorov axioms. The only one we haven't mentioned to this point is finite additivity. Mike says, to me, the key insight of probabilism is finite additivity. Finite additivity places demands on rational credence that don't follow from any of the norms we've seen to this point. To see how, look at the following two credence distributions over a language with one atomic proposition. Okay, so Mr. Prob is Mr. Probabilism, and Mr. Weak does something short of probabilism. So here's how to read this table. F is a contradiction. T is a tautology. I think we use the upside down T to represent a contradiction in the past. So you can think of this as an upside down T, this is a right side up T. Big T stands for tautology. So both Mr. Probable and Mr. Weak assign the minimal amount to a contradiction and the maximal amount to a tautology. So they satisfy that feature of the probability calculus. In addition, they assign probabilities so that there is no violation of the normality. Look at the names. There's no violation of normality. All the probabilities are between 0 and 1. There's no violation of contradiction. It's got the lowest amount both. There's no negative probability in place. And maximality is satisfied. Tautologies get the maximum amount. But now look at the in-between position. Tautologies are entailed by everything, and contradictions entail everything. So contradictions have to be lower than or equal to everything else, and tautologies have to be at least as high as everything else. So all of that is fine, but in between, we get this weird difference. Mr. Probable makes the probability of P or not P sum to 1. That's what we should expect, but it's not required by any of the previous rules. It's not required by normality, contradiction, non-negativity, or maximality. All that's required is that P and not P fall below T and above F. So what is it that we want from rational people beyond just satisfying normality, contradiction, non-negativity, and maximality? The answer is, if we want more, we want them to satisfy finite additivity, which Mr. Probable does. Notice the probability of P or not P is just the sum of what Mr. Probable assigns to P and to not P. But notice Mr. Weak is cautious here. He thinks, apparently, that P and not P don't exhaust all of logical space, because for all of the space occupied by P and not P put together, you get 1/36 of that space being assigned to P and 25/36 assigned to not P. That leaves some space unaccounted for. So Mr. Weak does not satisfy finite additivity. Mr. Probable does. So here's what Mike says about this. From a confidence ordering point of view, Mr. Prob and Mr. Weak are identical. They each rank not P above P, and both these propositions land between a tautology and a contradiction. They both agents thus satisfy comparative entailment. A quick note about entailment here. The only entailments that are present in this table, contradictions entail everything. Tautologies are entailed by everything. So the only links are from F to everything else, and from everything below T to T. And of course, T entails itself as well. All right, so they both agents satisfy comparative entailment. Both agents also satisfy the non-negativity and normality probability axioms, but only Mr. Prob satisfies finite additivity. His credence in the tautologous disjunction P or not P is the sum of his credences in its mutually exclusive disjuncts. Mr. Weak's credences, on the other hand, are superadditive. He assigns more credence to the disjunction than the sum of the credences in its mutually exclusive disjuncts. Now, why does he do that? Why does he say that? Well, remember, Mr. Weak assigns a credence of 1 to every tautology. P or not P is a tautology. So he assigns it a credence of 1. But the sum of the credences assigned to each of the disjuncts turns out to be less than what he assigns to the disjunction. So his credences are superadditive. He assigns more credence to the disjunction than to the sum of his credences in its mutually exclusive disjuncts. So he violates finite additivity. It doesn't matter if you describe it as superadditive or describe it in some other way, but he assigns a value of 1 to that, but the sum of what he assigns to the disjunctions is strictly less than that. And so here's the takeaway lesson. Probabilism goes beyond comparative entailment by exhausting Mr. Prob over Mr. Weak. In endorsing finite additivity, the probabilist holds that Mr. Weak's credences have an irrational feature not present in Mr. Prob's. Now, once again, you may balk at this use of the language of rationality. If you don't, you can take epistemology classes and you can learn to be cautious about when and where charges of irrationality might be appropriate. But if we substitute concern for getting to the truth over error, there's something strange about Mr. Week's credences, because if you violate finite additivity, in some sense, your credences can't be well calibrated with truth and falsity, since you're not summing your credences for the individual disjuncts in a way that lines up with your confidence level in the disjunction itself. Okay, so call that irrational if you want, call it less than ideal if you prefer less charged language, but there's something inadequate, something lacking, something less than ideal in Mr. Week's credences that's not present in Mr. Prob's. Okay, so the first step in tying our formal system to our epistemology, to the rationality of belief, or what kinds of belief systems or degrees of belief systems are most ideal. The first link is the notion of comparative entailment, because that's what we've been studying. It gave rise to most of the axioms in the Kolmogorov axiomatization of probability theory, but not to all of the axioms. The one that's left out, the one that gets you from comparative entailment to what probabilism requires, is finite additivity. That's what Mr. Prob and Mr. Week are showing us. If you want to get to probabilism, where it's something about the nature of mathematical probability that provides a necessary condition for being ideally rational or an ideal seeker of the truth, you need finite additivity in addition to the others. Okay, so that's the first step in getting us to probabilism. Now, the second step, let me stop sharing this because I need to pull up something else. Okay, so that's the first step. Now, after the first step, we want to know, well, if you satisfy all of the axioms of the probability calculus, does that make you rational? Is that what it really is to be a probabilist? We are now ready to ask, what is probabilism and what would enhancements of it be like? So I'm going to turn to the second page and come back to the first. So here's what we know about probabilism to this point. Probabilism, as I use the term and as most people do, involves two requirements. We've only looked at the first one. So there's one that's synchronic. It just holds at a particular moment of time. And the second is diachronic. So the first one says, how do you get yourself into an acceptable starting point? What is it to have credences that are rational in the first place? That's the synchronic requirement. So that's a requirement that holds at a particular slice of time. Call that slice of time T. Probabilists say you have to satisfy the axioms of the probability calculus, including the finite additivity ones. So Mr. Week, that we looked at before, is not in a good starting point. Mr. Prob is in a good starting point, or at least he satisfies minimal requirements for being in a good starting point, namely satisfying the axioms of probability calculus. So there are going to be synchronic requirements, but then, as you know, you learn more things as you live longer. You also forget things, but we'll talk about that later too. So the second requirement is, when are your changes in attitudes ones that are also ideal or rational? And for that, the probabilist adds a minimal diachronic requirement called conditionalization. So probabilism is a view that is constituted by both a synchronic requirement and a diachronic requirement. The synchronic requirement is that you have to satisfy the axioms of the probability calculus to be rational, which of course requires that you satisfy comparative entailment as well. But you also have to satisfy conditionalization. So what does conditionalization require? That's the first slide. So let's figure out what conditionalization requires of us. Assume then that we have a language L and a probability function PR, that for all well-formed formulas phi and psi of the language, it assigns values to phi, psi, and the conditional relationships between phi and psi as well. So it's complete with respect to the language. Every sentence and every conditional / relationship between sentences gets assigned a number by the function PR, and that number is between 0 and 1 and also satisfies the other of the probability axioms. Among the unconditional probabilities in this complete assignment is the total evidential state. So think about this just for you. You have little bits of evidence, some of them related to some of the things you believe and some related to other things that you believe. And now collect all of those little bits of evidence into one big conjunction. That proposition is your total evidential state. It is all and only what your evidence consists in. Now, what should your attitude be toward your evidence? Here's one idea. Your total evidential state is the state composed of all of the unconditional probabilities of 1. Take everything that you assign a probability of 1 to. Put it all together, that total evidential state will be a state of all and only things that you assign a probability of 1 to. So the idea here is that when you learn something new, you come to know something that you didn't know previously, and everything that you know should have a probability of 1. Now, none of what I said there is required by the probability calculus itself. But suppose we accept all of it as just a natural way of supplementing the probability calculus so that we can talk about evidence and credence states and the relationship between the two. So now we have a position that we are holding. Evidence is a state of all the things that you assign a probability of 1 to. We now want to know what changes are brought about when changes occur to your total evidential state. Well, remember, our total evidential state is the summation of everything that has a probability of 1 attached to it. So we model changes in question by investigating what happens when further learning is thought of in terms of becoming certain of something. So you don't know what's outside the window. If you learn that there's a cardinal outside the window, the way we understand what just happened is you become certain of the claim that there is a cardinal outside the window. That is, you come to assign a probability of 1 to the claim that there's a cardinal outside the window. All right, now what are we supposed to do to change your attitude toward all the propositions involved in the things that you believe or have credence attitudes toward? We look for a formula, E of the language, that represents the entirety of what comes to have a probability of 1 from the original point in time to the later point in time, about which we want to know how the probabilities change. So what we do is we look for a formula E that encodes absolutely all the new stuff that you learned, not just part of it. So if you learn that there's a red cardinal outside the window, part of that is that there's a cardinal outside the window. But that's not what we're looking for. We're looking for the maximal encoding of information of what you've learned, what you've come to assign a probability of 1 to. Now, what we do is we apply the rule of conditionalization. Conditionalization says to let earlier conditional probabilities guide. That is, where E is what is learned between T1 and T2, where T1 is earlier than T2, we let our new unconditional probability for a claim mirror the prior conditional probability on E. All right, now I want to go a little bit slowly on that because I described it in a way that is hard to process. So notice we have two different probability functions. First, we have the probability function at time t2. We also have the probability function at time t1. The second thing we have is that we're asking, what is this function, the second function, going to assign as the value for phi itself? And that's going to be a matter of what conditional value the first function assigned to phi relative to e. Now remember, e is not just a bit of partial information. E is the totality of what you learn between time t1 and t2. So it's inclusive. If there's anything else that you learned besides e, then this formula doesn't tell you what new probability to assign to phi after learning e. It's only when e is complete with respect to all the stuff that you learn. So the idea is this. Right now, you have certain attitudes toward what you would conclude if you learned various new pieces of information. So I don't know what day you're listening to this talk, but if you learned that today was Thursday, suppose today isn't Thursday. Suppose you know that today is Monday. That's something that I know today. Today is Monday. Well, what attitude would I take to the proposition that tomorrow is Friday, given that I learned that today is Thursday? Presumably, I'd become certain that tomorrow is Friday. But I am not today certain that tomorrow is Friday. In fact, I'm certain that tomorrow is Tuesday. So what I have in my head is certain conditional attitudes in addition to these unconditional ones. I have an unconditional confidence that of one, let's say, that today is Monday. And hence I have an unconditional confidence today that tomorrow isn't Friday, sorry, I changed the example, isn't Friday. But I also have a conditional attitude that I'm certain that tomorrow is Friday, given that today is Thursday. All right, now suppose I come to learn. At some point this week, I will come to learn today is Thursday. What should my new attitude be to the claim that tomorrow is Friday? Well, as long as learning that today is Thursday is the totality of information that I learned, then my new unconditional probability should be the same as my old conditional probability on the evidence in question. So that's called conditionalization. You treat new learning as becoming certain of some information, and then you update your probability to match, you update, creating a new unconditional probability that matches your old conditional probability. If you do that, you have satisfied conditionalization. And then, let me clear that. So you have to, some people, in fact, these notes make it sound like to be a probabilist, you just have to satisfy the synchronic requirement. I used to characterize it that way, and it's fine if you want to characterize it that way. My new idea is to be a probabilist, you satisfy the axioms of probability calculus, and then, so long as we're modeling new learning that way, you also have to endorse some diachronic requirement about how you change your point of view across time. And conditionalization is the right one when we model new learning as becoming certain of something. So, rational non-monic changes in view involve credences that satisfy the axioms of the probability theory and conditionalization, the diachronic requirement appropriate when we treat new learning in terms of becoming certain of the new information that we receive. Now, I'm emphasizing that latter point because you may question whether becoming certain of new information is the right way to understand learning. You may wonder, why can't I learn stuff without becoming certain that it's true? We will talk about that later. If you think of learning as not requiring becoming certain, then you can't apply conditionalization. Conditionalization can only be a requirement when we understand learning to involve becoming certain of something. So if that's not how you think of learning, just hold off. We'll get to something that might be more relevant to how you're thinking about learning. Right now, though, let's leave that assumption untouched. Here's a couple of things that we might do. We might question either one of these requirements. You might think, conditionalization, who cares? Even if you do model new learning in terms of becoming certain, I don't see why I have to obey conditionalization. That's one kind of objection. Another kind is, I don't really think I have to satisfy the axioms of the probability theory to be rational. Now, we've seen some reasons why probabilism, construed as endorsing the synchronic requirement, follows from the logic that we've had, because it looks like almost all parts of probabilism get supported by the comparative entailment requirement. And the comparative entailment requirement looks like a rather minimal link between the logics that we've studied and the question of the rationality of belief. So there's significant pressure on anybody who says, I really don't think the axioms of probability theory need to be satisfied in order to be an ideal seeker of the truth or rational. Probabilism, the one part of probabilism that comparative entailment doesn't connect with is, of course, finite additivity, but that didn't seem to be where people were going to balk if they were going to balk about probabilism. So let's just suppose we grant both of them. We then ask, what else is there that you have to do in order to satisfy the demands of rationality? We ask, do we need more? And for those who say, no, probabilism plus conditionalization are not sufficient, they look around for additional principles. So they offer additional principles. And then we can ask, are these principles any good? In other words, are they necessary for rationality? And also, suppose we add them to our package. We then add probabilism, conditionalization, plus your new principle. Is that all we need? Are they then sufficient for explaining the link between logic and rational belief or rational credence? Here's one. Now, we are going to prove this. This is one of the homework problems in the Teitelbaum book. Prove that if you update by conditionalization, certainties never disappear. That turns out to be correct. So once you become certain of something, you can never learn that you were mistaken. Once certain, you will forever and always remain certain. Now, as soon as you hear that, you should become a bit suspicious. I mean, just think about your own history. Haven't there been times in your life where you were absolutely convinced of something and then you found out you were wrong? It's an astonishing fact when it happens, but it's not unexpected. In any individual case, you're pretty sure, nope, that's exactly right. I will not come to find out that that's mistaken. And then you find out that that's mistaken and you're shocked. It happens to lots of people. To many people, it happened in the, what year did Kerry run against Bush? That would have been 2004. So the early polls had Kerry ahead by 20 percentage points in Pennsylvania, one of the disputed states. And many people went to bed saying, it's over, Kerry's won. This wasn't not even going to be close. And then they wake up the next morning and find out Kerry is not the next president. It took a little while for that to be confirmed. It had to go to the Supreme Court because of the Florida hanging chads and the ballots and things like that. But people who woke up the next morning and it was reported that Bush won the election would say, I was just certain that Kerry had won, but I was wrong. That seems like a relatively common phenomenon. When it happens, it's always a shock to you in the individual case. But that it happens is not a shock. It's not surprising that people become certain of things and later on learn that they're false. All right, but if you adopt probabilism plus conditionalization, you end up being unable to accommodate that. So maybe what we should insist is that you just don't become certain of anything that you don't have to. Now, the probability calculus requires that if it's a tautology, you assign a probability of 1 to it. So there's going to have to be some things that you assign a probability of 1 to. But notice, tautologies are not things that you can learn are false. So maybe that's the way to protect yourself. Don't ever become certain of anything unless the probability calculus itself forces you to become certain of it. That is, don't assign a probability of 1 to anything except necessary truths. That's called the regularity principle. Rationality requires never assigning a contingent claim, one that's not necessary, a probability of 1 or 0. No extreme probabilities for contingencies. Now, the problem is that regularity doesn't play well with conditionalization, so you have to give up one of the two. Why do I say that? Well, conditionalization works in the following way. You model new learning as coming to be certain of something, and then you update accordingly. But of course, if regularity is true, you don't model new learning as becoming certain of something, because you never become certain of anything except mathematical and logical truths. Okay, so conditionalization is never applicable if regularity is, or at least rarely applicable, because most all of your learning will not involve becoming certain of something. So if you adopt regularity, you're not really supplementing probabilism plus conditionalization. What you're doing is you're embracing probabilism, adding regularity, and throwing conditionalization out the window, except in very rare cases, namely where you're studying math and logic. So there's some tension between regularity and conditionalization. Now, the arguments for regularity, though, look pretty convincing. It looks like, first, you should be capable of being certain, but then learning you're mistaken. And it also looks like it should be possible to model learning without requiring that you become certain of everything that you learn. So maybe that's a reason for thinking regularity is perfectly fine, and restricting conditionalization won't get us in trouble. Okay, a second principle beyond regularity. This is called the principal principle, but it's spelled differently, as you can see in the two cases. Now, what motivates the principal principle is first, the history of interpretations of probability. So the axioms tell us how certain formulas involving probabilities are related to other formulas involving probabilities, but they don't tell us anything about the meaning of the term probability or the fundamental nature of what probability is. For that, you need a theory of probability, or maybe you need a semantics for probability. What are we talking about when we talk about probabilities? And here there have been 4 proposals. One of the earliest proposals was the frequency interpretation. A probability is just a statement of relative frequencies for certain events in nature. So what do we mean when we say the probability of a coin flip? The flip of this particular coin coming up heads is 0.5. Well, we just mean the frequency of the coin flip landing heads is about 1/2. Now, it's easy to see that something has to give. This can't be quite right, because first, the probability can be 0.5, but it would be really shocking if you flipped the coin, say 10 million times, and it came up exactly 5 million heads. So the frequency and the probability are going to diverge, almost certainly, as the numbers go up. That's one problem. The second problem is Some coins are never flipped, so there's no frequency, but nonetheless, there is a probability of it coming up heads. Here's another one. Some coins are flipped exactly once and then melted down and made into something else. Well, there the frequency is either 0 or 1, not 0.5. So frequency interpretations of probability quickly got replaced by what are called hypothetical frequency accounts of probability. Hypothetical frequency accounts say, with respect to the coin flip case, if you were to repeatedly flip this coin over and over again, the point on the line between 0 and 1 that the frequency would converge toward is 0.5. Hypothetical frequency accounts are much more promising than actual frequency accounts. But they have this weird counterfactual conditional. If you were to flip it an infinite or approaching infinity number of times, the margin of error between the actual frequency and 0.5 gets smaller and smaller. What are we to make of the antecedent if you were to flip it over and over and over? Counterfactuals are always puzzling. We haven't studied them much. You read a chapter, I think, in the Cider book about them. But one thing that happens is people bring up apparently irrelevant, but not actually irrelevant scenarios. So take a coin and say, if I were to flip it over and over and over and over again, more and more and more, some people will say, yeah, if you kept doing that, pretty soon the entire coin would wear away and you'd have nothing left. I don't know how many flips it would take, but there'd be nothing left to flip after you kept wearing away tiny and tiny amounts of microscopic particles, and then there's no coin left. So if you were to flip it a number of times as you approach infinity, there'd be no coin left at all. All right, now that in a certain sense is right, but it also doesn't seem to be very charitable toward the heart of what the hypothetical frequency view is trying to say. And the critic will say, yeah, well, that's a problem for the hypothetical frequency theorists. They need to be precise about exactly what they're talking about. They can't get away with sloppy counterfactual conditionals. They need to say more clearly what they're talking about. Okay, so that's a frequency view. A second view is that probabilities are logical. They're logical in the same way that all of first order theory is logical. And the best way to start this view is to start talking about something like the atomic propositions for a language, where you have a number of atomic propositions. You assume that they're all logically independent and that together they exhaust all of logical space. And then you apply something like a principle of indifference, and you say, in the absence of further information, we will treat all atomic propositions as equally likely. And then it turns out you're off the ground and you can assign probabilities to everything else. It's just a matter of simple logic. Meaning by that, honor comparative entailment and embrace the axioms of the probability calculus that are supported by that requirement, and then endorse finite additivity as well. And then you get all of the probabilities you'll ever need for anything. Unfortunately, the initial starting point is problematic. I don't know how you get to assume that all atomic facts are logically independent of each other. That's one issue. A second issue is this principle of indifference, that in the absence of information, you treat all of the possibilities as equally likely. We'll come back to the principle of indifference and the problems for it, because it plays a crucial role in the entire history of confirmation theory, which we're going to talk about when we get to chapter 6 of the Teitelbaum book. Okay, so you tried frequency and hypothetical frequency, you tried a logical theory. Here's another theory. Let's just identify probabilities with credences. So we will say a probability function is just a degree of belief function and nothing more. Now that's fine, except in all of these cases, and especially in the case of subjective accounts of probability, Science needs to be able to talk about something that's not a probability in that sense. It's going to need to talk about objective chances in nature. So the irreducible language of chance or probability is all over science. And it's not about how confident the investigators are of the truth or falsity of certain views. It's something that resides in nature itself. So think about the half-life of uranium-235. I don't remember what the number is, but there's an objective chance for any atom in a pile that it will decay within a certain period of time, which is the half-life of U-235. There's an equal probability in the half-life that it decays and that it doesn't. That's not about attitudes of the investigators, so it's not a subjective notion of probability. If it's a logical notion of probability, nobody knows how that would work. It's not about hypothetical frequencies, unless you can make sense of that more generally. Maybe it's about propensities. The pile of U-235 has a certain propensity or disposition. That would be an objective notion of chance that you could find in nature. But the problem is you have a mathematical notion of probability, and then you have this creature of mystery, which is a propensity or disposition that you find in things. And it's not as if you're clarifying something by appealing to something that's easier to understand. Rather, you're mystifying probability. Probability is a notion we use all the time. There are axioms that we can state governing probabilities, and then you tell me that we should really understand probability in terms of propensity. And the most natural response to have to that is you are clarifying in the wrong direction. If you told me we can understand propensities in terms of probabilities, I would have said, okay, that's good, because now we're taking the less mysterious and using it to understand the more mysterious. But when you try to explain probability in terms of propensity, you're going in the other direction. And that's a lousy way to try to develop your theories. Okay, propensity theories, by the way, trace to Sir Karl Popper. He's the most famous propensity theorist in the history of probability theory. So in any case, we have both probabilities and objective chances in nature. So for the moment, let's just forget the idea of trying to reduce all of this down to just one notion of probability. Let's go, for example, with the subjective notion of probability to understand why we're linking to credences. And then we'll also have objective chances in nature. And now the question is, should there be a connection between the two? If you have a certain credence level, what should be the credence level in comparison with the objective chances for that claim being true? Such principles, if there are any, will try to calibrate your credences with what's out there in nature. Now, what's clear is on anybody's account, an appropriate credence level doesn't have to match the objective chances in nature, because often you don't know what the objective chances in nature are at all. So to say that your credence should match the objective chance in nature would be to overstate any reasonable requirement on what your credences should be. So for example, suppose you buy a ticket in a lottery, right? A little Boy Scout comes up and says, we're holding a lottery. The winner gets this brand new car, gets a brand new car, and the cost of the ticket is $10. So you just want to be a good citizen, so you buy a ticket for $10. And then I ask you, how confident are you that you're going to win the lottery? And you suppose you have an attitude. I don't know where you got it from, but suppose you say, oh, I think my chances are 1 in 10,000. And then I ask you, what are the objective chances in nature that you win? You will say, I don't have a clue. I didn't ask how many tickets were being sold. I didn't ask what kind of a car it was going to be. I didn't check any of it out. I was just trying to be a good citizen. So you have a particular credence, and in all likelihood, it doesn't match up with the objective chances in nature, and there's nothing irrational about finding yourself in that position. So if we're going to link appropriate credence levels with objective chances in nature, we're going to have to be more subtle than that. How about if we think of it this way? Suppose you know what the objective chances in nature are. How should that affect what credence level you attach to the proposition? Now we're in a different position. So if you know it's a 100-ticket lottery and you know that you own exactly one ticket, you now know what the objective chances in nature are on the assumption that it's not a fixed lottery. So we assume it's a fair lottery. You now know your chances of winning are 1 in 100. How should that affect your credence level that your ticket will win? And now it seems like we have a really good explanation of how the two link up. Your subjective credence level should match what you know the objective chances in nature to be. That's what David Lewis thought. He wrote out his formula this way, where the probability sub h is an initial reasonable credence function, t1 a time, x some number between 0 and 1 inclusive, and the chance of a at time I, bx. Here's what David Lewis thought. The simple version is this. Your, let's call it credence rather than probability, your credence in A, given that the chance at the time in question of A is x, should be x. So the crucial thing is the two values line up. And that fits in terms of a conditional probability, what I described in terms of knowing what the objective chances are. So if you knew that the objective chance in A for A to be true was x, then your probability for A should be x. What if you don't know? Well, still, your conditional attitude should be this. My conditional attitude in A, given that the chance of A is x, should be x. And then if I learn that the chance of A is x, I will update just in the way I do with conditionalization. If learning involves coming to assign a credence of 1 to the claim, then if the only thing I learn is that the chance of A is x, I will change my unconditional credence in A to match what I learned the chance was. That's the motivation for the principle. Now, there's a problem for the principle. It sounds plausible, but it turns out maybe it overreaches a little bit because it lets your knowledge of chances control in a way that you might not always want it to. Suppose that you know that the suppose that you know the chances of A, it's somewhere between 0 and 1, and not an extreme probability. But you've also heard the voice of an angel, so that you know that A is true. So the angel told you the chance of A is 0.6, but A is true. Now, what should your credence be? Well, the answer is that you should be certain, so long as we're assuming that you know that what you know involves a credence of 1. To avoid cases like this, David Lewis restricts the principle to cases in which you change your credence only by way of changing your opinion about its chances. He says that's what makes the information admissible. Now, we're going to come back to this, so I'm not going to spend a lot of time on it in this lecture. We're going to come back to the principle and the notion of admissible evidence when we talk about the homework in the Teitelbaum book. So once we factor in admissible information, the new principle says this, where you have a certain initial reasonable credence function with the same understanding of the times and the chance symbols. Let E be a proposition compatible with this chance claim that's admissible. Then the conditional probability that you should assign to A, given that the chance of A is x, together with information E that's admissible, that should be X. So it's a more complicated version. We'll wait to talk about this in more detail when we get to the homework in the Teitelbaum book. Now, notice that what the principle is asking you to do is to defer to chance. If you learn, in general, if you learn what the chances are, that controls the credence that you now attach. The question is whether chance is the only thing or the unique thing that you should defer to. What else might you want to defer to? Well, just think for a minute. What or who do you defer to in general anyway? You don't always update your credences. You don't always explain learning on the basis of information that comes through your senses alone. You learn in other ways. So one thing you do typically is defer to experts. Well, suppose you want a principle that has you do that, where the credence for A is X, says that the credence of expert E regarding A is X. So this reads, E is an expert, E's credence for A is X. The expertise deference principle would say your conditional probability on A, given that expert E's credence regarding A is X, should be X. Notice that's just like David Lewis's principle. He advocated deferring to chance. This one advocates deferring to expert E. Now, you should worry about the expertise deference principle because remember, E is a unique expert. How many experts are there? There's lots of them, let's assume. Do they all agree about A? Presumably they don't. What are you supposed to do when you get a bunch of experts and they don't all agree with each other? Well, the expertise deference principle tells you to defer to each of them individually, just change the subscript. But that's a little bit goofy because you can learn that E assigns X and then you change your estimate. You change your credence in A to match to X, but then you learn that expert number 2 assigns something different than X, and so you change to that. And you keep going back and forth or from accommodating one expert to accommodating another, and that doesn't really make any sense. So maybe you think I need to agglomerate. I need to figure out what the expert opinion is. Think of that perhaps as the average expert opinion. And that's what I'll defer to. But that doesn't seem rational either. The average expert opinion is often not something that you should defer to. There's no particular reason that the average is correct, whereas each of the individual experts are ones that are incorrect. So there's lots of messiness when you start trying to defer to experts. That falls under the general epistemology of testimony. And you can see that this is going to get complicated very fast. A third reflection principle, though, involves just you and yourself. Do you trust yourself? Now, if you don't trust yourself to discover the truth, you are in a sadly self-undermining position. Without having some trust in yourself and your ability to figure out what the truth is, you will never have grounds to alter your opinion, change your opinion, come to a different opinion. So let's suppose you do trust yourself. And suppose you also think that you have a bright future in terms of getting better and better at forming rational credences in light of your evidence. You might have the other view too, but let's go with the optimistic view for now. You have a bright future. Not only will you learn lots more new things in the future, but you'll also get better at figuring out what the truth is and at figuring out what are the appropriate attitudes for you to have in light of your evidence. Or suppose you think something like this. Here's another one. Integrity demands that you fully commit to the ways in which you will rationally revise your opinions and values over time. So right now you're sitting still and you're asking yourself, will I think the same things tomorrow that I think today? And the answer is probably not. Some of them will be the same, but we expect your opinions to shift over time. We also expect the same of your values over time. What counts as most important to you today will likely not be the same as what counts as most important to you 10 years from now. That's very good. Now ask yourself, do you think you will make these changes over time in rational ways or irrational ones? Are you going to try to be rational, or are you going to fail to try to do that? Are you just going to have changes happen to you and you really don't give a shit one way or another about whether you revise rationally? Presumably you think, I'm committed to making rational changes to my opinions and values over time. Okay, that seems like the right way to think about yourself. You probably also know that you won't succeed at that, but that's what you've committed yourself to. You have committed yourself as a human being to make rational changes to your opinions and values over time. That's what you're trying to do. And it looks like that's what it is to be a person of integrity. Who could be a person with integrity who says, no, I'm just not gonna, that rationality stuff isn't for me. I'm gonna make changes, but I really don't care if they're rational or not. That looks like a person without integrity. You ask, well, what are you gonna do when you make those changes? What's gonna motivate you to make the changes that you make? Is it gonna be, say, complete self-interest? So you're willing to turn yourself into a complete bullshitter as long as that serves you, your interests. You'll change your opinions and values so that they turn out to serve your self-interest in that way. Is that what you're after? That seems like a person lacking in integrity. And when you start thinking about what alternative ways there are to commit yourself to in terms of the changes that will happen to you, it looks like it's very hard to avoid committing yourself to rational revisions if you're going to be a person of integrity. So let's suppose that we endorse that. I am going to be a person of integrity, which means I'm committed to rational revisions. All right, if so, then you might wish to defer to your future selves as well. Think of it as deferring to somebody who's better informed on the subject at hand. So where credence sub j is later than credence sub I, reflection tells you to do this. Set your later credence at time A to match what your earlier credence for A was, conditional on your credence in A being X. Set that to X. So if you view your later self as having a certain attitude toward A, then your current attitude toward that should be A as well, once you know that your future self is going to have that attitude. In the absence of knowing it, all we have is the conditional attitude that your later credence will match what your earlier conditional credence was. That's reflection. So we've got three principles. We've now got regularity, which conflicted with conditionalization. We've got the principle, and then we have two versions of deferring to experts kind of opinion. One is where the expert is another person. This one, the reflection principle, is where the expert is your future self. Finally, there's the indifference principle. Maybe we want to add this to the story so that when you have two claims and no information about whether or why one of them might be more probable than the other, then you just split the probabilities between the two. More generally, count up all of the possibilities, all of the ways that the logical space in question could be divided. It could be just two, but it could be 10 or 15 or 20, whatever it is. In the absence of any information whatsoever, count all of that up and divide by the number of possibles. So if n is the number of positives, then 1 over n is the probability for each one of them in the absence of further information. The indifference principle is due to Laplace. He said, so long as nothing leads us to believe that one will happen rather than the others, we should apply the principle of indifference. And this worked its way into the early stages of confirmation theory in the work of John Maynard Keynes. Keynes wrote, the principle of indifference asserts that if there's no known reason for predicating of our subject rather than another of several alternatives, then relatively to such knowledge, the assertions of each of these alternatives have an equal probability. Note the value of such a constraint. Unlike the other principles above, it covers every other situation in which one might want principles in addition to probabilism and conditionalization. Now, the principle of indifference faces a certain kind of paradox.